So to give some physical basis for the critical plane approach, I'm going to go over a paper from my own advisor, Daryl Socie, Critical Plane Approaches for a Multi-axial Fatigue Damage Assessment. And we'll talk about some of this here. This is an ASTM paper. And we'll get into some of the details of how to implement a critical plane approach in a separate lecture. All right, so this paper starts off with talking about the fatigue damage process, and it goes back to Ewing and Humphrey's paper back in 1903, and we've talked about this one in this class. It says the course of the breakdown was as follows. The first examination made after a few reversals of stress showed slip lines on some of the crystals. Slip lines were quite similar in appearance to those which are seen when simple tensile stress exceeds the elastic limit is applied. After more reversals of stress, more slip lines appeared. After many reversals, they changed into comparatively wide bands with rather easily defined edges. So this is the metal fatigue process that we had talked about. And so from that perspective, we have the slip systems forming, the persistent slip bands, and eventually shearing at the tips of cracks, causing an extension in the crack surface. What you'll often see is kind of a crack surface that kind of goes up and down as it propagates. So you may not really be able to see this with the naked eye, but these are basically the striations that we get from the crack tip as a crack moves across the surface of the material. All right, so as we read a little further, and I'd like for you to read this paper, it is available to you on our box folder. Early multi-axial fatigue researchers, such as Go and others, proposed an empirical relationships that reduce the shear stress for ductile materials and principal stress for brittle materials. Go's ellipse quadrant is often cited and is given here as an example. So here we have a combination of shear stress amplitudes in a material parameter, tau f, and axial stress amplitudes, sigma a, and other material parameters in here. So it's a combination of shear and tension. The applied tension and shear stresses are given by sigma a and tau sub a. Fatigue limits and tension are denoted by sigma f and tau f. No physical interpretation was ascribed to this equation. When the ratio of fatigue limits and torsion and bending equals to 0.5, the expression reduces to the maximum shear stress criterion. Similarly, the maximum principal stress criterion is obtained when the ratio is equal to 1. And then Stullen and Cummings proposed a model that considered the interaction of the ranges of maximum shear stress and normal stress on the maximum shear stress plane. Okay, so when we think about multi-axial, don't think of only the components of stress, sigma x, sigma y, sigma z. Think of all the stresses on all the planes and all the material at the same time. You can have in-plane and out-of-plane maximum shearing stresses and so forth. It's the entire stress tensor that you're really keeping track of all at the same time at that particular point. So in this one, it was sigma 1 minus sigma 3 over 2 plus some function of sigma 1 plus sigma 3 over 2 is equal to a constant. Here it says where sigma 1 and sigma 3 are the maximum values of the largest and smallest nominal principal stress during the loading cycle. Constant fatigue lies are a function of the maximum shear stress range modified by the normal stress range on the maximum shear stress plane. The effect of normal stress is included through the constant g. If the constant g was selected to be equal to 0, the criterion would be the maximum shear stress. Similarly, if g is equal to 1, we'll give the maximum principal stress. Here again, a single criterion can be made to fit both the cracking modes described above by a suitable choice of an adjustable constant. It is not surprising that these theories consistently fit the data. And now we get down to the next section here. Based on physical observations of the orientation of initial fatigue cracks in steel and aluminum, Findley discussed the influence of normal stress acting on the maximum shear stress plane. A critical plane model was introduced. Tau a plus k sigma n maximum is a constant. For a constant fatigue life, the allowable alternating stress, the shear stress tau sub a, decreases with an increase in the maximum normal stress, sigma n max. So let's pull up our notepad here. So if we have a particular plane in a material, so here's my stress element or my stress block, with my multi-axial stress state on it. If we were to look at maybe one of these planes, then the important parameters involve the shearing stress amplitude. Okay, so this would be a history, and the normal stress acting on that plane. Okay, and from a cracking perspective, that makes a lot of sense. If you're shearing and causing that initiation, and in addition have a tensile normal stress on that plane at the same time, then you can develop cracks more quickly and more readily on that plane, as opposed to another plane that didn't have the same high value of tensile normal stress. Okay, and then we get into case A and case B cracks. I'll let you read through that. And again, here's the orientation of the shearing plane. You could have an in-plane and out-of-plane situation going on in all these different possibilities when we have the multi-axial loading. So if you're familiar again with Moore's circle, probably talked about an in-plane and out-of-plane absolute maximum shearing stress, and these are considerations that we have in fatigue as well. All right, so let's read through this next section kind of carefully. AISI 304 stainless steel was tested in tension and torsion. The type of cracking behavior exhibited is summarized in the next figure. The stainless steel tested in torsion. Right, cracking behavior could be categorized in two regions, region A and B. Region A behavior was observed at short lives. Microcracks initiated on shear planes. Once initiated, the cracks became more distinct, showed no significant increase in length. At failure, a large density of small coarse cracks dominated the surface of the specimen. Small amount of branching onto tensile planes or stage 2 planes was observed. Failure, cracks grew on either shear planes or tensile planes by slow linking of the previously initiated shear cracks. Region B is characterized by shear crack nucleation, followed by crack growth on planes of maximum principal strain amplitude. Shear crack growth consumes a small fraction of the fatigue life. Region C behavior was observed at the longest lives in torsion. The fraction of life spent growing the crack on shear planes was reduced, as was the crack density. Small number of cracks initiated on shear planes but quickly branched to stage 2 planes. Growth on these planes occurred by propagation of the main crack rather than by a linking process. Let's take a look at this figure and we'll try to put those words in context. Okay, so here's the stainless steel in torsion. Okay, so here's our specimen. Okay, we have a crack that is here. This would be on the shear plane of the specimen. So if you think of the tube going, I'm going to assume it's going to go horizontal. You could have a shear plane that initiates in this direction if we have torque and the thing's going that way. Let me see if I can go back to my sketch pad. Now I may have the direction of the orientation of the specimen incorrect, but it wouldn't affect what's going on with the cracking plane, because if we have our tube like this and we have it in torsion, the maximum shearing planes are going to be both up and down and this way. All right, so we have region A. This is the short fatigue lives, and this is the life fraction. Then we have the region B over here. in this region, in this part of this damage mechanism map, we have growth on the tensile crack planes. Now, when you have cyclic torsion, the maximum principal stresses are at 45 degrees from the axis of the bar. And so you have a combination, when you cycle it in torsion, both those 45-degree planes could initiate cracks. And we see that in this picture as well. Now, this damage mechanism map, part of this is for if we were to take a particular life level, like 10 to the 3 cycles, some of this is consumed in crack nucleation, and then the remainder is in shear crack growth. If we were over here on the high cycle region, we have a larger percentage of the life consumed in crack nucleation. Then we have tensile crack growth, and we could also have a region where it goes through this dotted line. You can have a combination of nucleation, shear crack growth, and then tensile crack growth, depending on the plane that you're at. Okay, here's the 304 stainless steel. This time the test was in tension. We have similar kind of behavior, crack nucleation, and in this case, tensile crack growth. And then he went on and did the same sort of thing with Inconel 718. There's a little difference between the two materials. Okay, so here's the Inconel 718. In this case, we have the shear crack growth, not much tensile behavior. Now this is in tension. We have some shear crack growth and tensile crack growth, crack nucleation, and so forth. Okay, so one of the points that I want to make with this is that different materials can exhibit sensitivity to different damage mechanisms depending on their load level. And different load types. What this means for us is that we may need to use different damage parameters for different materials. We also may need to use different damage parameters for different types of loading and different loading lives. All right, well, let's try to read a little bit further in here. And he also did a 1045 steel. Once the failure mode has been identified, an appropriate life estimation model can be selected. Each region requires a separate damage model based on the observed failure mode. Okay, that's just what we wrote down. The following damage models are proposed, although it is important to note that alternative models could have been chosen. The models selected, however, must incorporate the dominant or controlling parameters for each region, as those below do, such as shear strain for region A, tensile strain for region B, shear stress or strain for region C. And so we have the region A damage parameter. Okay, this region is dominated by plastic shear strains. Shear strains alone will not correlate the results from tension and torsion tests. Torsion tests have longer lives when compared to tension tests cycled with the same shear strain. The conceptual basis for a damage model is shown schematically in Figure 6. During shear loading, the irregularly shaped crack surface results in frictional forces that will reduce the crack tip stresses, thus hindering crack growth and increasing the fatigue life. Normal stresses and strains will separate the crack surfaces and reduce the frictional forces. Fractographic evidence for this behavior is shown in Figure 7 from tests on the Inconel 718. The torsion test fractograph shows extensive rubbing and is featureless in contrast to the tension test fractograph, where the individual slip bands are observed in the fracture surface. Following damage model may be interpreted as the cyclic shear strain modified by the normal stress to include the crack closure effects described above. So he has gamma times 1 plus k sigma n max over sigma y. It's a maximum normal stress on a particular plane modified by the yield stress, and then it's equal to some parameters that have the reversals and some material constants in it. The material constants are primarily determined from the shear test, so we have tau f prime over g plus gamma f prime, which is analogous to what we used for the strain life equation. This model was first proposed by Fatimi and Socie. The right-hand side, a description of the strain life curve from torsion that we just said. The terms on the left-hand side represent the loading parameters defined on the plane experienced the largest range of cyclic shear strain, having the following definitions. Gamma is the maximum shear strain amplitude. Sigma n max, the maximum tensile stress perpendicular to the plane of maximum shear strain amplitude, normalized by the yield strength. To preserve the dimensionless features of strain, constant K is usually equal to unity. All right, so there's the figure. Okay, now here we have a model for region B. Cracks nucleate and shear, then grow on a plane perpendicular to maximum principal stress and strain. And what we have is a Smith-Watson-Topper type parameter. Sigma max epsilon is equal to sigma f prime squared over e times 2 n to the 2b plus epsilon f prime 2 n to the b plus c. And then region C, this region is typically called the high cycle fatigue region. The majority of the fatigue life is consumed by crack nucleation on planes of maximum shear stress or strain for ductile materials. Finley's model can be combined easily with the description of the material's fatigue resistance to describe fatigue damage in the finite life region. So here we have tau A is equal to K sigma n max is equal to tau F prime 2 and F to the B. Of course, what we have is more sensitivity to the high cycle region. We don't have a lot of plastic straining going on, so we're using just the material property tau F prime. Now, also to note here, it says for low ductility materials such as gray cast iron that are dominated by flaws, a shear model is inappropriate and consideration of principal stress and flaw size is needed. Fracture mechanics approaches for these are suggested. So now this is a real interesting part, and one that I like to highlight to my students that are doing testing down in the lab as a way in which some very thoughtful analysis ahead of time can help out when you go to do your testing to highlight the effects you're trying to show in your whatever damage parameter or whatever your test is trying to do. Never go in the lab and just try to test something. Always have an idea of what you're trying to first hypothesize and then prove or disprove based on your thinking through the details. Okay, so let me read a little bit of this. Influence of mean stress. Several sets of test data were reviewed to demonstrate the effect of mean stress. Inconel 718 specimens were tested with 6 loading histories that are shown in Figure 8. Loading histories are shown in terms of the applied shear and axial strains on tubular specimens. Details of the testing are given in reference 25. Now, they were designed to have the same maximum shear strain amplitudes. Histories D, E, and F have cyclic proportional straining with a static mean strain and would not be classified as non-proportional straining for purposes of fatigue analysis. The experiments resulted in nearly the same maximum shear stress amplitudes, equivalent stress and strain amplitudes, and plastic work. The major difference between the loading histories is the normal stresses and strains across the plane of maximum shear strain. Observations of the specimens show that all the tests had cracks on the plane of maximum shear strain amplitude. Mohr circle of strain, shown in Figure 9, shows the two perpendicular planes experience the same maximum shear strain amplitude. Okay. right, so here we have our more circle and we have our maximum shear planes. Let's see, probably ought to read a little bit more here. If fatigue damage was determined by shear strain alone, the two maximum shear strain planes would be damaged equally since the strain state is the same. Recall that the sign of the shear strain has no physical meaning and is used only as a sign convention. Figure 10 shows that the cracks are formed for these histories. The orientation of the crack pictures is the same as the shear plane shown in Figure 9, except for loading history C. Cracks form on only one of the two maximum shear strain planes. History C represents compression, loading where cracks form on both shear planes. The compressive normal stress inhibits growth of the initial cracks, which allows more time for cracks to form on the second shear plane. The shear plane for history E is minus 20 degrees rather than plus 20 degrees because the loading direction is reversed from the other histories. Fatigue lives are given in Figure 11. Even in a proportionally strained test, the stresses do not pass through zero at the same time, since the principal axes of stress and strain are not coincident. Thus, mean stresses on the two shear planes are not equal. The open symbols of Figure 11 represent the maximum normal stress shear plane. Solid symbols represent the lower normal stress on the other shear plane. Okay. All right, so we have maximum normal stress, we have failure plane, and the non-failure plane. Okay. And here in this picture is the influence of the cracking plane on those different mean strains depending on the histories that we have. As you see, many of these are very much the same, even though the path looks a little different. But some of these with compressive strains show a little bit different behavior. All right, so let's see. Mean stress affects not only the growth rate of the cracks, but also the distribution of cracks. Two tests, 0 to tension and 0 to compression, are considered here. The compression test, the normal mean stress on both shear planes is compressive. Multiple cracking is observed on both shear planes. Many cracks nucleate but have difficulty growing. Fatigue lives are greater, so that more cracks have an opportunity to nucleate in grains that have crystallographic slip planes oriented near the maximum shear plane. Finally, a dominant crack forms on the shear plane that has the lowest compressive mean stress and grows to failure. In the tension loading case, cracks are observed on only one of the two shear planes. The first cracks to nucleate can easily grow to failure. Little secondary cracking is observed. Extensive observations have been made for these tests. Mean stresses have a lesser influence on the initiation of a crack if crack initiation is defined on the order of 10 micrometers, which is the size of the smaller grains in the material. The stress and strain ranges, as well as the equivalent stress and strain ranges, are the same for all 6 loading histories. Mean stress effects have been demonstrated even in the life regime controlled by plastic strain. Energy-based approaches such as plastic work and strain approaches that do not consider mean stresses predict that all loading histories will have the same fatigue life. This is clearly not the case, and the use of these approaches must be restricted. All right, so even though the area of your hysteresis loop may be the same for those different types of loading paths, it's more than just energy that comes into play. Mean stress definitely has an effect on the fatigue life. Okay, so then there's some discussion of hydrostatic. Let's see, let me find another section of this paper. Okay, in this section, I want to read this in a little bit more detail. With this background, it goes on and talks about cracks and the observations. With this background, we are now in a position to suggest a series of critical or discriminating tests to clearly establish the influence of mean stresses. Consider a tubular specimen that can be loaded in tension, torsion, and internal pressure. Now remember when we first started talking about multi-axial, we said that we could have tension, torsion, and we could have internal and or external pressure. That allows us to get a hoop stress. not only does that allow us to get a hoop stress, but it allows us to play around with the angles in which the maximum shearing stress can occur. All right, the baseline test will be torsion. Materials that exhibit extensive mode 2 shear cracking are expected to have a distribution of damage as shown in figure 15. Cyclic strains are shown with double-ended arrows. Both shear and tensile strain planes are indicated by the dashed lines. Expected cracking directions are also indicated. All right, so let's see, figure 15. All right, so if we have pure torsion, we would expect to have straight up and down cracks and horizontal cracks like this. This is the planes of maximum shearing strain. The maximum tensile strain is at 45 degrees to it. Okay, so the shear damage would tend to look like this, vertical and horizontal cracks, where the tensile damage would tend to be an X-shaped crack. Let's go up a couple pages and read some more. Cyclic strains are shown as double-ended arrows. Both shear and tensile strain planes are indicated by dashed lines. Expected cracking directions are also indicated. Adding static tension would introduce a tensile stress on only one of the two shear planes, indicated by the single-ended arrow in figure 16, and be expected to reduce the fatigue life from the case of torsion alone. Static tension will not influence the stress on the vertical shear plane, and no damage is expected on this plane. Static tension will result in increased stresses on both tension planes. The addition of the static tension will be detrimental for both materials that fail in shear and for materials that fail in tension. Okay. So let's look at this one. So if we were to add tension to this cyclic torsion, then we should expect only cracks that are horizontal for the shear damage, but that shouldn't have any influence on the tensile damage crack morphology. Now consider the case of static compression with a cyclic torsion. The horizontal shear plane will have a compressive stress, but this beneficial compressive stress will not increase the fatigue life because the material will fail on the vertical shear plane. All right, so now we have cyclic torsion and a compressive axial stress. Well, this plane right here is benefited, and the cracks then should look straight up and down. But there's no change in fatigue life because this situation and this situation, it's the same damage mechanism. You're just forcing which plane is going to be the one that's going to be damaged. Now for tension, whether it's in compression or not, for tensile damage, it looks the same. All right, both tensile planes will see the beneficial effect of compressive stress. This critical test suggests that the compressive stress will not have an influence on the fatigue life for materials that fail in shear and have a large influence for materials that fail in tension. Finally, the fourth test case is presented in figure 18. Internal pressure is added to produce a hoop tension stress and compression generated by the axial load. All right, so now we put in a hoop stress. We have axial compression. In this case, the tensile stress on the vertical shear plane is detrimental, and the compressive stress on the horizontal plane is beneficial. Naturally, the expected fatigue life will be reduced and the failure will be on the vertical plane. The two stresses will combine and cancel each other on the tension plane. In this critical test, the shear damage material is expected to show a large influence on the static stresses, and the tensile material should be unaffected. This is exactly opposite to the loading case presented in figure 16. Fatigue models must be able to distinguish between these two loading cases in materials. Results for tests conducted on NCL 718 are given in Table 2 and confirm the discussion above for materials that fail in shear. And then it says, unfortunately, no tests are yet available for materials such as cast iron and fail in tension. And that was at the time of this paper, which was in the early to mid 90s. All right, so, and it goes, the rest of the paper goes on and gives some detail about more of these tests that were conducted. All right, so the big point then I like to make with that, other than the points that we've already made, is that when testing, examine the entire stress state and see if you can have a set of discriminating tests. If you have an idea about how cracks form and why they're forming on these particular directions, see if you can influence that behavior by doing different combinations of tension and torsion, static compression, static tension, cyclic torsion, and then in the cases where you can do internal pressure, that also adds another dimension of how you can influence this cracking behavior. So with all these different things, we can get an idea of not only maybe when the crack can form, but what the mechanisms are that create their initiation and their propagation. All right, so I always like to kind of go over that paper in a little bit of detail. I haven't shown it all, haven't read it all, and I think it's a really nice paper, has some good pictures in it. Download it off our Box account, find it in the ASTM website, and have a nice read going through that paper.